Alright guys, get started, yeah. Alright, soil mechanics. This course is known to be pretty hard. I'm honestly not the most qualified person to do this because I'm not like a geotech guy, I'm more like a structural guy. But there's overlaps, you know, so if you're interested in like kind of structural stuff or the fluid stuff, this course is kind of a mix of that and more. Yeah, as you probably know, Aman, he loves to just pack heaps of shit into this course, and I don't think he's ever cut any of it, even from like when the course used to be like semester system and everything, where there was like 12 weeks to study everything. Yeah, it's all still in there. But with that said, some of the topics are like groundwork or like foundational, and they build on like each other, and the questions which are presented in the exam, these ones, yeah, you can kind of see patterns, you know. So there's stuff like phase diagrams, 2D seepage, settlement, triaxial tests. These things are pretty common. I've heard from Dom that last year there's actually 5 questions, but each part, like there was less parts for each question. And they slipped in a slope stability question, which is the last topic. I'll try my best to cover that, but I don't have a question prepared for it. It'll more be like theoretically kind of cover it. But these ones will be the ones that I'm focusing on. I probably won't have as much time to focus on phase diagrams today, because phase diagrams requires a lot of like practice, but it's not very much theory. It's actually more like a 2101 kind of question. You just kind of need to know about like general soil properties, but it's more like how much dirt do we need to move from here to here, and like how much water do we need to add in. It's very like construction, like engineering construction kind of questions. So I'll be trying to cover everything from question 2 to 4, so seepage, settlement, triaxial tests, etc. Yeah, but even each of these topics, like they build off of heaps of foundational skills which was covered throughout the course. So like 2D seepage would be building off of 1D seepage. It'd also be building off of like effective stress. And that just kind of goes for everything, and I'm not just gonna yap about that for too long because we'll just kind of see it as we go into it. But with that said, I think the first thing I want to talk about today is effective stress. So I know like your exam is issued on Friday, right? I've heard. So it doesn't give you very much time, right? But I understand that like, you know, you probably just like handed in like big assignments or something for your other courses recently. So everyone's at a different stage. Like if you're already up to the stage where you can do like practice questions on your own, it's really good. But like I'm kind of going to run this workshop in the context that you know essentially nothing about this course, except for the fact that you ran like, you had to do like the 3 quizzes or whatever it was, right? All right, so we get started with that. So yeah, the first thing I'm talking about is effective stress and stress. Sorry, give me 30 seconds. I'm gonna blow my nose. Actually, they're right here. Okay, all good. So the idea of effective stress and stress, this is basically the equivalent of like bending moment diagrams or like, you know, shear force diagrams, that kind of thing for structural. This is like 1D stress, right? So this is like the most important concept to understand about this course. So as you know, stress, right, is the force divided by area, right? That's just the general concept. So it's about a force that's spread out over some area, basically, right? So in the context of soils, right, the most important type of stress, well, not most important, but like the first one you learn about is like an axial stress, usually in compression, because when you step on soil, you're compressing it. And when you step on soil, you're using your gravity, using your weight to push down on it. So it's like a vertical stress that you're applying to, right? So we have to think about it in terms of like a weight distributed over a certain area, right? Yeah, so that's what vertical, like when you see sigma V, that's referring to, you know, vertical stress, right? There is a way to express it in terms of density. So density is rho, gravity, and then H is like the height of soil, right, compressing onto itself, right? So you can imagine as you get deeper and deeper into soil, there's more soil above it that's pushing down onto it, right? And then there's an increase in stress. So that can also be expressed in terms of gamma. So gamma is basically these two things combined, right? So gamma is unit weight, it's your density multiplied by your gravity constant. And then Z, right, is usually the notation we use in this course. That's the depth of soil, right? And so to a certain point of interest, right, so on the left here, say it's like we care about some 0.4 meters below the ground. Yeah, there's 4 meters of soil like stacked on top of it, essentially, right? And this is for a soil that's all the same unit weight. So that's 20 kilonewtons per meter in this example. You can kind of graph it vertically, right? So, you know, plotted vertically. So this is why I'm saying it's similar to a bending moment diagram and shear force diagram, right? It linearly increases as you go down, right? So it'd be 80 kPa of essentially pressure, right? But we call it stress, stacked on the soil there vertically, right? Okay. So in a slightly more complicated example, you might have different soils of different unit weights. So usually you have the heavier soils at the bottom. They kind of like naturally form lower. And then you have lighter and lighter ones, right? So as you can imagine, the graph for this kind of increases, like the gradient increases as you go down, right? Because the unit weight starts getting stacked higher and higher, right? So, you know, you'd have a greater gradient essentially, right? Okay, the other thing to keep in mind is soil expresses stresses in different directions, and we usually care about vertical and horizontal stresses. Because vertical, because we step on soil like vertically, so to get like vertically compressed, right? Horizontally, you'll find out in geotech, which is the next course after this, in term 1. You'll have like you'll have like retaining walls and stuff like that. And it's very important to understand the concept of like horizontal pressure when you like, because that's what's going to cause like sliding and overturning on that retaining wall, right? So like soil can also kind of cause this horizontal pressure, right? Anyway, so the way you calculate horizontal stress is you need to calculate the vertical stress first, right? Which is what I described just a little earlier. And then there's something called the coefficient of lateral earth pressure. You'll see when we talk about triaxial tests how they kind of derive this constant. But essentially, it's just a number, let's say around the ballpark of 0.6. It depends on the soil. It's soil specific, right? That relates how much horizontal pressure is happening versus how much vertical pressure, vertical stress it was experiencing, right? Do we have any questions so far, by the way? Okay. So next, in the context of water, right? So how water interacts with soil is incredibly important. But generally, like the most important thing you have to keep in mind is that water will make soil weaker, okay? So it might seem a little bit counterintuitive at first because of how we talk about effective stress. So the concept of effective stress is the formula for it over here. Effective stress, which has a little dash, right, is your stress minus the pore water pressure, okay? Okay, so we talked about stress already, so that's that component. We can also graph the pore water pressure, which starts at the water table and then goes down, and it's based on the unit weight of water, right, which is 9.8. Okay, so let's think about this quickly. Okay, if I have like a box that's filled with air or whatever, right? And then I push it in, you know, compress it from like all sides. Is the pressure going to increase or decrease? It's going to increase, right? Say that box is full of air, or it could be full of water, whatever, right? That's like an increased pressure. So the idea of soil, right, is that it's a porous material. So it has all these little voids, some of them are full of air, some of them are full of water, stuff like that, right? Pore water pressure is all these pores, right? And then they have pressure from the water, right? And when you have when you start hearing the words like excess pore water pressure, it means that the pore water pressure is increasing for whatever reason. Like it could be like the soil could be getting squashed or something like that, and then the pressure within the pores increases, right? So anyway, so that's pore water pressure. Okay, but yeah, in like hydrostatic conditions, which means the water's not moving, It's 9.8, right? Yes, is there anything else to say about that? No, it's always 9.8, but it's based on, yeah, the depth of water, right? And it increases linearly as well with the height in hydrostatic conditions. So that's going to change when we look at 2D seepage a little bit, okay? Okay, so lastly, yeah, so effective stress, I've finally gotten to it. It's basically these two graphs subtracted from each other. So it's the red graph minus the blue graph is equal to that purple graph, right? So you shave off the water pressure. Okay, so you're thinking about, okay, the effective stress, effective vertical stress is lower, right? After you add in water. So surely that means that there's less stress in the soil and it's stronger, right? But later you're going to find, when we talk about the shear stress, the shear strength of soil, right? Your shear strength of your soil is basically how sticky or how much friction the soil has with itself, right? And it's a function of your stress. So if you have more normal stress, it's actually going to be stronger, right? So that water is kind of going to act as like a lubricant and then weaken your soil because it's going to slip and fail and shear. Yeah. Okay. Any questions so far? So I haven't even gone to an actual question yet, but like hopefully this theory kind of makes sense because this is the foundation of the entire course. Like every single question is based on this theory, right? Okay. If that's all good. I also just want to quickly say sometimes you'll have different coefficients of lateral earth pressure for different soils, right? So if it decreases, you might find that there'll be a sudden jump in your your horizontal stress. Yeah, in that graph, right? Okay. We'll get to that later. So I'm gonna quickly talk about phase diagrams, but I'm not gonna focus on this. There's a worked example here. So basically, in that folder, right? So if you scan that QR code, I have my notes here, which is called Soils Recap. And then there's also the 2022 paper, the 2021 paper, and the 2020 paper, right? I don't have solutions for all of them, right? I've only got solutions, which is what's in this Soils Recap for 2021. They're not official solutions, but they're my friend Clarissa's solutions, and she has a 95 WAM, and they're basically 100% correct. But the other ones, you can see what the questions look like, but I don't have, I don't have solutions for them. Okay, so phase diagrams here. Basically, the idea of a phase diagram is that you have two kind of general areas that you're working with. The first one is the compacted fill. This is basically a hole that you want to fill with dirt. Okay, that's it, right? Okay, and then the other one is your borrow. So borrow, you think of this as like an infinite pool of dirt that you can get soil from. Doesn't matter what it is. It could be a quarry, it could be whatever, right? So you have like essentially an infinite volume, okay? So within this borrow, we have something called a test pit. Now the test pit has a limited volume, right? It might be like 50 meters cubed or something, right? It's a big enough sample that it's going to average out to have the same soil properties, right, as the like the infinite size borrow, right? The idea of all these questions, basically, they're all going to be practical. They're not going to ask you anything that's super stupid. The idea is that we want to fill this hole, and so it will ask you usually questions to do with how much volume of the soil should we extract from the original borrow in order to fill this hole with these properties that we want, right? And then it's also just asking about stuff like how much water should we add in as well. So yeah, it's usually about finding the volume, all that stuff. Okay, so I've got some questions, right? We're looking for the volume, right? And we want a certain moisture content, I think. Sorry, one sec. Yeah, okay, sorry, it's written here, right? they specify how much volume we want to fill the hole, because we know how big the hole is, right? They specify the saturation ratio that they want the final mix to have, right? The mix of soil. They also specify how many voids should be in your soil, right? So these are all properties. We work backwards from the final solution to your borrow's properties, right? They tell you the borrow's properties. So the test pit, has like all this, but it has a certain moisture content, right? So like 10.25, we have to add a certain amount of water to it. I'm not explaining this that well. Give me a sec. Okay. Yeah, what I'm trying to say is that the test pit and the borrow are going to have a certain moisture content and other soil properties, and they're going to be shared between the overall borrow and the test pit, right? But obviously the volume is going to differ, the mass of the soil is going to differ because we're dealing with different quantities, right? Yeah, and so that's the general concept you have to like think about when doing all these questions. The fact that there's kind of these two circles and then a circle within one of the circles, you know what I mean? Yeah.
Does the mass of solid stay the same? Going from?
The ratio will stay the same. What percentage of the soil will be solids, and what percentage of the soil will be water and air will stay the same between these two things. But the actual mass is a function of the volume, right? Yeah. So like you can think of it like, that stuff, that ratio is going to stay the same between, solids, water, air. I think you get it.
The shooters have said that the mass of solid always the same for compaction.
Sorry.
Because if you're just compacting the solid should stay the same, but the volume.
Yeah. What I'm trying to say is that the mass of the solids in the infinite volume borrow is going to be infinite, like effectively, right? But then the mass of the solids in the test pit is going to be a set number. Yeah. But the ratio of what these two would be relative to the mass of the solids, the mass of the water, the mass of the air, that ratio will stay the same. Do you get what I mean? Yeah. The other thing when you're doing these, so the actual phase diagram itself is gonna like help you kind of navigate all these like random ass numbers, right, that you have to just slowly fill out. It's good habit. I know I just drew the mass on the left-hand side, but it's good habit to develop either drawing the volume, like writing the volume numbers all on the left side and then the mass on the right side, or vice versa. But just keep it consistent so you don't mix it. It'll make it faster for when you're actually doing your finals. Yeah. Do you have any other questions for the moment?
Question about the effective stress.
Yeah.
If you want to switch between vertical and horizontal, we say multiply by k.
Yep.
Right?
Okay.
What if you want to switch effective stresses? If you want to switch from effective verticals to effective horizontal.
I see what you mean. What do you mean by that? I think it's all like.
I remember him saying you can't switch between effective horizontal and horizontal. You have to use effective vertical to get effective horizontal. And you just multiply by k not again.
Yeah, because it should be the same ratio, right, between these things. Is that what you mean? Yeah.
No, the formula in the lectures is effective vertical equals k times effective.
Okay.
No, effective horizontal equals k times.
I could be wrong. I just looked on Google for this formula. But like, I don't know. If it's in the lecture, sure.
Should be the same though.
Should be the same, yeah. Yeah, like it's the same ratio, right?
Yeah, it's just times by the same ratio.
The ratio is always consistent. As long as you're consistent and you use total. I'm pretty sure you said you can't switch between one of the horizontal and effective and horizontal.
All right.
No. So if you're using effective, you're trying by effective.
Let's get on to our first question, guys.
Yeah.
All right, so basically, the first question that we're going to cover is question 2. That one will be 2D seepage, right? So, let me start without the flow note being here. Okay, so here's how a question is typically presented in the exam, right? Basically, here's concrete, right? So this is impermeable material, we assume. On the left-hand side here, we have water that's elevated, right? and then over here, the water table's at the ceiling of where the soil is. And yeah, we have impermeable rock here as well. Okay, cool. So the annoying thing about this is that you have to pull out a ruler and you have to convert from a centimeter to IRL meter scale. Okay, so that's the first thing you got to do. That's here, right? Because the first question is basically just draw the flow net, right? It doesn't say draw the flow net, but it says you need to develop a flow net first, and it gives you marks for it, right? So that's what we're gonna do. Let me see the exact numbers it was. Yep, so based on the A4 print from the 2021 exam, this is a 1.6 centimeter scale, right? So this, let's call it the paper scale. That's basically your, yeah, like your ruler, and that's what's on your page, right? Now, the scale, what it turns into, right? What that distance actually turns into. This was based on your ZID, and I think this is based on like COVID times. So they had something called a mega, right? Which is just the last two letters of your ZID. Here, I didn't want to directly provide my friend Clarissa's solutions because I don't want her to get pinged for academic misconduct. So basically, I just consider omega as 50, right? So that's the number we're going to go with. So when you plug that in, that gives you 5.5 meters. So 1.6 meters, 1.6 centimeters, sorry, on the page results in 5.5 meters in real life, right? And so that goes for all the dimensions that you measure on your flow net here. Okay, so that means this height here, we measure it as 2.26 centimeters, right? And we're gonna draw a flow net now, right? So the idea of a flow net is that essentially we have equipotential lines and we have flow lines, right? So I like to start with the flow lines. So flow lines go parallel to how the water's flowing, right? I'm gonna try to recreate this. It looks something like this. Yeah. Okay. So I know it just looks like I drew some random fucking lines, which is what I did. But like, the idea of it. Oh my god. The idea of it is that we try to kind of equally think about like spacing, I guess, to the best of your ability. I didn't draw it perfectly here, but you kind of want these spaces to be roughly the same, right? When you're drawing your flow lines. And then we're also going to draw perpendicular lines, right? And these are called your equipotential lines. So these lines represent areas with equal amount of energy, I guess you can say, right? So you're going to lose energy as the water flows through your soil, right? The general assumption of seepage is that we're not in fully hydrostatic conditions. Hydrostatic conditions is where the water's not moving at all. We're moving at a very slow hydrodynamic kind of speed, right? So we don't have, when we're talking about energy, we don't have any velocity head, right? Because the velocity of the water is so slow. But we do lose energy, yeah, as we go through the soil, right? Okay. Draw some lines. Oh my goodness. How many did I draw? Okay. 1, 2, 3, 4, 5, 6, 8, 9, 10. Yes. Okay, cool. So the idea is that we were trying to make these as square as possible, or like the ratios as even as possible, right? So obviously someone is going to draw this flow net different than me, even for the same question, right? So if you drew the flow lines closer together, right? So if you had more flow lines because they're drawn closer together, so you had 5, right? The idea is that you will also have more of these perpendicular lines as well, right? It's all about that ratio of how far the water has to flow across versus perpendicularly how many channels it has to flow across that area, right? Does that kind of make sense? Okay, cool. So that's drawing the flow net. So we were given some stuff like information, water content, and we're also given the coefficient of permeability, which is little k, right? I've just converted it, so it gives it to you in centimeters per second. I've converted it to SI units, so meters per second, right? Okay, so NF and ND, this is based on your flow net drawing, right? So NF is the number of flow channels you have. So that's not flow lines, right? I drew 3 lines, which were the parallel ones that ran through the page. Flow channels is how many squares you have, right? That are running, parallel. Someone want to tell me what that is? Very good. And ND is the number of drops, right? So that's how many squares going perpendicularly, right? So I counted them across, it was 10. Okay. So so again, that's based on the flow channels and the number of drops, so 4 and 10. Cool. So now, the first thing we have to do is find the overall difference in head, right? So we don't know how much energy is in like the total system because it will vary a lot, and we're just looking at this isolated system. So delta H is talking about what's the difference in energy from our region of higher energy to the region of lower energy in soil. So basically the water is going to be flowing left to right, essentially, right? So, okay, how do we know how much energy has changed when we go from here to over there, right?
Just the drop of water.
Yeah, very good. So it's 5.5 meters. Sorry. Okay, basically what we measured was 2.26 centimeters, right? That's what we measured here on the left, right? And we're going to use something to convert it from our centimeter scale to our meter scale, right? So we're going to do we're going to multiply it by our new units, right? So 5.5 meters, and divide it out the old units, which is 1.6 centimeters, okay? So that's our way to convert from centimeters to meters and scale it by an appropriate amount. Yeah, do you have a question?
Sometimes in a couple of questions for the number of drops, he does like 9.3 or 0.4 because the number of drops is not exactly 1.1.
Yeah.
Which square would we look at? 12, middle, bottom?
I would recommend sticking to an integer just because that level of accuracy is not going to be required for an exam. Yeah. You'll definitely get full marks of integers. Yeah. Okay. So when we multiply that all through, right, we get 7.6875 meters, something like that, right? I've just kept it as a lot of decimals. I'm sure if you do a bit more rounding than what I've done, you still probably get full marks. But I've just kept it, yeah. All right, cool. So now we can actually solve for the flow, right? So this is a modification of Darcy's equation, right? This one here. Darcy's equation is all about basically calculating the flow of water through a permeable material like soil, right? So a material with a lot of holes in it, essentially, right? This is the version for 2D seepage specifically, okay? So as we calculated before, we converted what we were given, the coefficient of permeability, and we converted it to meters, so that's why it's to the power of -7. And then we also just calculated the head, right? So that's in meters, right? So we're dealing with the right units. And then NF and ND was our number of flow channels and number of drops, right? So that's 4/10. That gives us 1.243 times 10 to the -6 meters cubed per second, yeah? So that's the first step. Okay, great. Next, we calculate the head loss per drop. So that's just a matter of how much head, right? Difference in head from like the start of the system to the end of the system was. And then we're dividing it by the number of drops, right? So the number of drops was the perpendicular lines, and it loses energy at each stage, right? It loses energy probably more like linearly, but we just are gonna consider those set intervals, right? So that's our total change in energy per head. Sorry, our total head divided by the number of drops, right? Easy peasy. Okay, let's look at the wording of B, right? So compute the pore water pressure and the hydraulic gradients at points A and B shown in the figure. So for reference, A was here and B was here. Yeah. So yeah, that's what we're gonna do. We'll focus on A first, right? Okay. So let's talk about point A real quick, yeah. I'm just gonna redraw a couple of these lines because I did it differently in my solutions. More like that vibe. Okay. So you know, we have whatever amount of head here, and then it drops by our delta little h each step, right? So would you say that in order to find the head at A, right? H, I think. In order to find the head at A, would we consider this line or this line? In between, right? That makes sense? Okay, so how far in between? So that's where you have to pull out your ruler again. So you have to pull out your ruler again and find the ratio of how far across your square that line has gone.
But that's only when we have a scale, right?
Yeah. So I measure 0.95 centimeters across that square. Just a bit quieter, please, guys. All right. So, and then for the entire square, that's 1.2 centimeters, yeah? So it's all about that ratio of how much it is across. The good news is all we care about is the ratio. So we don't need to multiply these numbers by our conversion, right, back to meters, because that'd be a waste of time, right? So we can just do 0.9 divided by 1.2. That's the ratio of how many squares across that one. So that's what we're going to do over here. I've called this like purple box just for explanation's sake, but we've gone 5 drops across, right? Plus 0.95 over 1.2. That's how many, yeah, that's how many squares across we're going to consider it as, right? We might as well do the one for B now as well. So, yeah. Basically, we measured this one as 0.5 centimeters. We measured this one as 1.1 centimeters, yeah? Like that. And so we're going to count 8 drops across, and then 0.5 divided by 1.1. That gives us 8.4545, okay? Great. So here's how it works in terms of how the numbers plug in. So essentially, we're going to start at the area with higher head, right? So that's what we calculated before, right? That's how many meters of head we had at the start of our system. And it's going to drop by the, like by the drop per head multiplied by how many squares we're going to do, right? So that's what I was trying to do in purple here, right? So this we calculated, head per drop. This we calculated, that's the ratio thing that we did. That gives us 3.2694. Yeah. So that's our total head. Okay, next is our elevation head. Basically, we're trying to get to the pressure head. That's what we're trying to work out, and then we're going to try to use that to get our pore water pressure. So in order to do that, we need to know the total head, right, which is big H, and we need to know the elevation head. So elevation head, in terms of, if you remember like 1300 and stuff like that, that's the water equivalent of, you know, like mgh, whatever, gravitational potential energy, right? So it's all about your verticality-ness, right? So that's why we do another measurement here, right? That measurement is 1.1 centimeters, okay? We'll do the same thing for this one here, which is point B, because we're going to need it later anyway. That's 1.75 centimeters, right? So this one we are actually going to have to convert to a meter scale, right? In order, you know, it has to go from centimeters to meters. yeah, the idea is that we have a negative elevation, right? Because we go from our datum down. So it's 1.1 centimeters, but we have to convert it, right? That gives us a negative elevation head, right? Okay, we know that this is the formula for our head, right? It's the combination of elevation head and pressure head that equals our total head. And as I mentioned earlier, in seepage conditions, we essentially don't have a velocity head, right? Because we don't have that half mv squared, you remember 1300? We don't have the actual like kinetic energy of the water going through, because it's going through so slowly that it's negligible, right? We don't care about the speed of the water. Yeah. Anyway, so we rearrange that, and we want our pressure head, right? So that's just a matter of plugging in what we've already solved. That was 3.2694. And that was a negative number. So basically our pressure head is actually going to be higher than our total head. And that's because of how our elevation head was lower, I guess. So it's increased pressure. Okay, so here's where we get to pore water pressure. So this is kind of going back to what I was saying earlier about effective stress, pore water pressure, all that stuff, right? Normally, pore water pressure is kind of this unit weight of water multiplied by our depth of water, that kind of thing. But that's only in hydrostatic conditions. So as soon as we have kind of like a dynamic situation where we have this kind of seepage and suction, this is actually not going to be the case. This is going to be our pressure head, okay? Which is what we calculated earlier. So it's all good. So that's what the question asked from us. Well, one part of what the question asked from us. That was the pore water pressure, yeah? Next was the hydraulic gradient, okay? So hydraulic gradient is basically head per drop divided by how far it has to flow through that square, okay? So basically, we have a bunch of different squares, obviously, right? We have this square, we have fucking this square. The square we care about is the square which contains point A for hydraulic gradient. Now, hydraulic gradient is probably a more complicated, complicated kind of gradient when you use like computer analysis software and stuff like that. But in our method, which is doing this on pen and paper with 2D seepage, we can only calculate the hydraulic gradient per square. So it's kind of like, you know, like year 11, you're like learning about calculus, how there's instantaneous gradient and average gradient. We're doing like an average gradient. So what's the average gradient of this particular square kind of thing, right? That's what I is. Well, it's not quite what I is. I is basically kind of like a change in energy over that distance, right? So we're not thinking of it as like two physical dimensions relative to each other. We're thinking about energy loss, you know, over that distance, right? But yeah, as you can imagine, we're gonna need to measure the distance of that fucking square, which we've already actually measured. So it's 1.2 centimeters, right? But we do have to convert that back to meters, right? So we've calculated delta H before, and we measured this before. We just have to convert it back to our meter scale. Yeah, and then our hydraulic gradient is going to be a unitless kind of number, right? Make sense? I'm not going to bother doing it again for B because it's the exact same process. Yeah.
Change in head there is only one step, right? Not the entire.
Yeah. Because we care about how much energy is lost across this square. Do you know what I mean?
So you use small h, not
Yeah.
big h.
Yeah, definitely use small h. So if you wanted to graph this for whatever reason, which you definitely don't have to in an exam, this is kind of like the total length, right? And then this is your head. It's basically these steps which the gradient changes a little bit each time because of how wide the squares are. And then yeah, depending on the channel that you're focusing on, these will be different as well. So it kind of gets a bit tricky, but that's one way you can think about it, right? Does anyone else have any questions for now? Yep.
For the distance between the squares, earlier you said that make sure they're the same distance from the top.
Yeah, the idea is you want to try to make it the same, but if you look at this shape, right?
More narrow towards the top.
Well, we care about this dimension, right, L?
Yeah.
Yeah, so I know I didn't draw it perfectly like this way, but more importantly, it's these ones.
So towards the middle, try and make the squares the same.
Yeah, as best as you can draw it, but there'll be a large margin of error, so Aman's going to give you full marks if you get the process right. Yeah. But yeah, obviously we're not using the computer software, we're using our pen and paper, so there's going to be a huge degree of error. Yeah, it's just expected, but still try to draw it to a reasonable degree of accuracy, right? Okay, we're gonna keep going. I'm going slower than I was expecting. Okay, compute the effective stress at point B, right? So this time they don't care about point A, we're just gonna look at B, right? So this is one of those formulas that you learn in the first part of the course. It's kind of like a soil property kind of formula, right? We're just going to plug everything in. So in the entire exam, they'll tell you just take the specific gravity of your soils to be 2.65. So this is basically how many times heavier your soil is compared to water, right? You can expect it to be a little heavier because you'd imagine soil will sink in water, right? So like concrete is like 2.4, 2.5. Soil is 2.65. That's just the number we take because that's like a pretty good average, basically.
Always assume it's 2.6.
Unless it's specified otherwise. Even at the start of the exam, in like the first few lines, they'll say assume 2.65 for specific gravity unless specified otherwise, and assume 9.8 for gravity. Yeah. Do you have a question? Okay. Unit weight of water. Again, we assume that's 9.8. And this kind of wraps back to what we were given in the question. I know we haven't looked at it in a while, but just trust me, the moisture content was actually given in the question, so we don't use that until part C. Gonna keep plugging shit in. That's also the moisture content, and then this is given. Okay, great. So this gives us our saturated unit weight of soil, right? Yeah, saturated is important because water's like the entire thing's just submerged with water, right? Because we have the water table, the entire thing is saturated, right? So we use that formula. From our previous part, right? So part B, we calculated that the pore water pressure was this. Okay, now we kind of use that understanding of the 1D stress thing that I was talking about earlier to calculate the vertical stress, right? 1.75 centimeters is this, right? So that's that. So we measured 1.75. And we have to convert it, of course. And then we have to multiply that by the saturated unit weight, right? So that's 20.14466, right? Gives us 121.183 kPa. Okay, the effective stress, right, is just literally the difference between these two. So I'll just copy it. Yeah, and that's all the question asks from us. We move on. Okay, and then D, evaluate the exit gradient and compute the factor of safety with respect to the quick condition. Comment on factor of safety, appropriateness, stuff like that. Okay, so I'm going to quickly talk about what quick condition is. So, you know, like quicksand, right? I think pretty much everyone understands the idea of quicksand, but it's caused by an upwards flow of water that causes suction that goes down, right? And so when we look at our diagram, what point are we expecting this kind of quicksand effect to occur at? Someone want to take a stab at this? Where do you expect quicksand to occur, or like this quicksand kind of effect? Would it be in the middle of soil somewhere? Technically, yes, but the way that we kind of consider it in terms of like a engineering safety point of view is it'll always be at the surface somewhere, right? Yeah. So essentially what I'm trying to get at is that it will occur here. Okay. So this is kind of based on how you drew the lines and stuff, but generally the lines are kind of smaller in width over here than they are over here. If that makes sense, if you draw it like perfectly, right? So essentially we only care about the closest square, right? That closest square there, and it's the exit square. So it's where the soil is touching the water and the water's flowing up from. Do you know what I mean? That's where you're going to experience quicksand. And these squares are going to be less critical than the innermost square, right? So this is the point which you'd first see quicksand kind of effects happening, right? Which is what we want to design around, right? Okay, so essentially what we do is we measure the length, right? This delta L of this exit square, right? Because we're gonna calculate later the exit hydraulic gradient. So that requires L, right? Delta L. That was 0.8 centimeters. Okay, we'll keep that number in mind for a bit later. But we're going to calculate two formulas, right? So this is the first formula here, and blue. Here's the other formula. We're going to compare these two because we're going to do a factor of safety ratio check. I'll explain what that means in a second. But we literally just plug in everything that we know in order to get the critical hydraulic gradient. So this is calculated in the previous step. 9.8 is the unit weight of water. This gives us 1.0556, right? And yeah, basically the hydraulic gradient in reality, this is where we focus on that last square, right? Where the quicksand effect will occur first. So that's where we measured 0.8 centimeters, right? Yeah, just a second ago. Convert it by our scale. And just keep in mind this is your exit square, right? The length of the final drop. Okay, so how factor of safety works, right? So some of you guys might have already done concrete or steels, probably not too many of you, but like in structural design, right, we have to, so imagine you're designing, this is the example I always talk about. Imagine you're designing like a scaffolding, right, for some tradies, whatever, you're doing like false work. And you have 3 tradies, let's say they're kind of fat, they're like 100 kilos each, right? How much strength would you design this false work to have, right? The scaffolding. Would it be 300? Would you design for 300 if you're expecting 3 tradies to sit on it? Or like stand on it or whatever? You design the strength to be a bit higher, right? Versus the load in reality that you're expecting, right? So in structural design, like that's the idea of structural design. This is in the context of concrete, real quick. Don't write these formulas down. But this is called the this is called the structural equation. In the left, we have our external loads. On the right, we have our capacity. So all that's saying is that we have to exaggerate our loads by a bit. So you pretend that the tradies are like a little bit heavier than they actually are. And then the capacity is, you have to reduce it. Because you have to pretend that your steel, what were we talking about? Scaffolding. Your steel scaffolding strength is a bit weaker than it actually was, right? That's what you deal with in steels. That's what you deal with in concrete, right? Geotech's a little bit different. It's the same, but it's just presented differently. I don't know why. This is how they do it in the Australian standards, right? They do it in terms of factor of safety. So generally, you have your capacity, and then you have your external loads, and it's a ratio of each other, right? So when you're designing for a factor of safety of, say, 3, for example, right? Let's say that this is like a health bar kind of thing, and then this is the capacity that your soil or geotechnical structure can handle, right? What we're saying with a factor of safety of 3 is that this is the max amount of loads that's allowed on it, right? 3 times less than its actual capacity. So the reason this is presented like this is because this would be like, how do I say it? Soil is incredibly unpredictable, right? So you're gonna deal with factor of safeties in the ballpark of 1.5 minimum, all the way up to like 5 and stuff, right? Or higher, right? So when we're dealing with, back to hydraulic gradients and stuff, we're dealing with a factor of 5. That's the number we're gonna design around, okay? Which means that our health bar, right, has to literally be 5 times less than what we expect. I'd say capacity, but this is like almost like the ultimate amount, right? This is like once it happened, yeah. Anyway, that's like a safety thing, right? Okay. So we do this formula, right? We take the ratio of the critical, right? So critical being like the ultimate point where you start seeing like quicksanding and stuff like that, and divide that by what it is in reality, right? And in this particular case, right, with my ZID omega is equal to 50, right? I got a number that's greater than 5. I don't know if they still do omega in your final exam. I don't know if you have to calculate whatever, but like with Clarissa, my friend's solutions, this number was less than 5. This is like 4.78. So they'll kind of design the number so that some people will pass the check, some people won't. Just keep that in mind. So if you walk out of the exam, you're like, hey, did you like, in this question, like, did you pass this check or not? You'll have half the people saying yes, half the people saying no. You know what I mean? Anyway, so when it's greater than 5, that means we pass the check. So this is safe against quicksanding, right? This is called this quick condition. Okay, makes sense? Okay, so I'm going a lot slower than I'm expecting, but we might as well take a break now. I'm supposed to finish at 1, but it might low-key be pushed a little bit. Yeah, so we'll take a quick 5-minute break now. Go grab some water, go to the bathroom, and yeah. Yeah, man. So apparently last year it was these 4 questions and a 5th one, which is flexibility, but it's a really short question. And the other ones are a little bit shorter to compensate for time. There is a chance. I don't have notes ready for it because I ran out of time while preparing, to be honest. But I can give you the, like later, I can give you the general theory behind it, and it'll be a good foundation.
Thank you. That's strong like 32. They're the same project.
Stress. Stress. It's the one we did in the last. Apart from that, is there anything else that makes sense?
I'm actually, I won't lie, I'm doing better than I expected. It has nothing to do with civil. No.
I don't know what this one's called. Okay.
I'm genuinely seeing someone just talk about it. It wasn't right. It got me through.
This one.
That was the diagram.
Wait, is that
What's that?
Oh,
it's like wait, no time. You can ask for sure.
This one I'm not sure about.
I don't actually know.
It might be the only environment.
Is that bad? I thought this one was okay, just come on. And then let's try this one. Like slight stability and visual.
Oh,
Yes, sir.
shit.
And learning what's you need to basically rearrange
This goes as it's only one
and also rearrange this. Yeah. You rearrange this into you rearrange this and then now the sigma 3 but you also need to do this in terms of the sigma 1 becomes this as well, and then you rearrange it into this. And then you rearrange these to find delta U, and then you use delta U to rearrange like
Alright. You guys ready? I'm ready, Habibi.
This is the part. This is the part.
How many people in there?
Consolidation and Triaxial.
Yeah.
Wait.
I think more likely to ask that than the
reckon like you can assume base level like understanding of like how soil kind of. I'm kind of catering for like play with mud, but no, like they can understand like the feeling and texture.
So there's a lot of
Like for example, cohesion in sand. Everyone understands that. Because obviously sand is hard and falls apart. Like,
yeah, I'll split it up.
Alright guys, take a seat please. Take a seat, Hayden. Take a seat.
Alright, we're gonna keep running. Okay, so the next type of question we're gonna cover is consolidation. Here's what I'll show you what the exam kind of questions will look like. Then we'll jump back to the theory, and then we'll go back to the exam question, right? So here's how it's presented. So we basically have 3 layers of soil. We're looking at a cross section here. We have gravel at the top, we have clay in the middle, and then sand at the bottom. Essentially, whenever you're dealing with this consolidation question, right, we care about the clay, okay? And I'll tell you why. Okay. So for context, these are from my geotech notes, but that's why like a lot of this stuff's crossed out, because some of it isn't covered in this course, right? It's going to be covered in the next course, right? It's going to be covered in geotech when you do it in term 1. But settlement is a concept that like we're only going to talk about in the context of consolidation, right? So I want to present this to you because it gives you a better idea of what settlement is in general, right? So settlement is essentially about the displacement of soil, so how much it gets compressed together over time, right? So there's immediate or elastic settlement, right? But we don't cover that. That's mostly a thing that happens with sands and gravels, stuff like that. We focus in this course on consolidation, and most of the time we're talking about clay, right? And then this is a creep, which is like very, very long-term settlement, but we don't deal with that in this course either. You can look at these formulas if you want. This is all to do with elastic immediate settlement, which isn't in this course. Okay, so we're going to talk about consolidation. The first step is essentially finding changes in stress for various loading cases, right? Which I'll tell you how to do when we actually go through step by step. Oh, sorry. There's a few different methods to do it, right? The one that they've presented in this exam question in particular is the 2-to-1 method, right? Okay, firstly, let me just give, because we talked about stress, I probably said stress like 50 times already today, but the stress type that we're talking about in the context of consolidation or settlement is change in stress. And change in stress is basically the increase in stress after you load your soil, right? So if I put something heavy on it, or if I remove that heavy object from it, that's change in stress. This is like loading, right? So like a building, for example, chucking a Leaning Tower of Pisa or whatever, and then it, you know, okay. 2-to-1 method is one way to account for this, right? It's a pretty simple formula. You can see the formula here. Which is why they kind of prefer it, is assuming that this kind of, the stress kind of spreads out as you increase like your point of interest further and further into the soil at a slope of 2-to-1. And then there's a bunch of elastic methods, which were covered in this course. I haven't seen it in the exam questions yet, but it's not out of scope. This stuff is not out of scope, so I've included all the notes for it, right? The first one's Busnick method, right? And by the way, you have to consider what each of these little dot points that I've put in, like ABC and stuff, actually mean, right? So concentrated point load, right? That's like if I put this pen or something, which you can think of like as a point load, into mud, right? Or whatever. It's like piercing through it. That's what a concentrated point load or something would be, right? That's what these formulas are for. This is the geotech version. You might not, this isn't on the slides, but if you rearrange this, I guarantee you get the same thing. You care about NB in this course, right? Which is this one. NB is this line, right? And then, yeah, you calculate this number, you go to the NB line, you go down, and anyway, yeah, sorry, you'll figure it out. I think it's this way around, and then you'll find n. N's what you plug into this thing, right? Anyway, sorry. Probably do this one actually. Sorry, this is geotech. It's probably not the same thing. Okay, the next type of loading is a uniform strip load. So strip footing. Oh, sorry, there's also a uniform line load, but even Aman in his lecture slides says don't focus on line loads. They're really, really rare. A line load is like if I put like a sharp blade that is like 10 meters long into the ground, like, you know what I mean? Like a 1D load like that is really, really rare. A uniform strip load is more common though. It's like a 10-meter long wall, right? And like, say it's built out of bricks or something. The bricks have a certain thickness, right? So that would be like a strip load, right? Something like that's more common. Yeah, and there's also circular area loads, right? So circular footings are relatively common. Yeah, so like the footing in a building and its foot shape is like a circle, right? So that's, yeah. Again, I'm not going to cover these in depth because every single one is going to require you to read a different graph, stuff like that, right? Rectangular area load. I think this might have been in one of your quizzes, right? Maybe. Yeah. So, yeah. Sorry, I'm not going to cover these because we're going to run out of fucking time. Essentially, though, if you have a point of interest that's outside of your square. So if I have a building, right, and the point of interest is over here, you're basically going to need to superimpose your, because this formula only works from like corners, right? So you have to like superimpose like this and then subtract this off and then subtract that off, or add this on and then subtract this back off. You get what I'm saying? Yeah. That's kind of how these formulas work, right? Okay. Yeah, this one's even shitter. This is Newmark's chart. This is your point of interest here. Your building's like fucking here. You literally like count the number of square. He's not gonna make you do this. That's what Newmark's chart is. Okay, anyway, so that's change in stress. So what we just talked about in step 1 was delta stress. Now, you have to find the initial stress, right? Which is what we can do using, do you remember that thing? Stress analysis, right? Effective stress analysis. So you do that minus pore water pressure is equal to this one. That's what we care about, right? And then say that's your point of interest, that deep into the ground, whatever. In these formulas, they're usually called sigma I dash because we care about the effects of time with consolidation. So it's kind of implied that it's vertical, right? So we are talking about vertical stress because settlement's all about gravity going up and down, right? But initial because there's a very time-dependent component to all of the consolidation kind of stuff, right? And then the final effective stress is basically this one. And then you add on your change in stress due to loading or whatever, right? So if you add a building on top of all this, right? You add those two components together and then you get your final stress, effective stress, right? That's kind of the whole idea of this. Yeah, the rebound index, compressive index, this will make more sense when we do the question. There's a formula for total settlement. Total settlement is basically how much the soil will compress, how much the soil layer, so say that's the compressible layer, how much it will basically squish over time due to loading. Yeah, Faha?
Is this CR, CC, and delta PC, sigma PC dash always given?
Sometimes you have to calculate it. You'll see in the question actually. Yeah, I think you have to calculate the rebound index, but the compressive index is given in the question. Sigma PC is to do with, okay, maybe I should explain this. Basically, you can you can have two types of soil, right? I realize all this is actually probably more complicated to look at on your first glance, so don't focus on that for the moment. Basically, I'll explain normally consolidated soil and over consolidated soil first. Normally consolidated soil means that the soil is experiencing like the highest stress that it's ever experienced at the moment, right? So it hasn't previously been compressed any further or like stressed any further than it has. This is normal soil. So this is like, you can call it virgin soil, right? Sounds fucking weird, but like virgin soil, like out in nature and stuff, usually that's normally consolidated soil because it hasn't been stressed further than it actually has. Over consolidated soil is basically where it previously has experienced more stress than what it currently is experiencing. So for example, if there was a large rock on some soil and then I took the rock off, that's now over consolidated soil, right? Because we've alleviated some of the stress, right? And yeah, what the stress that it's experiencing right now isn't the highest stress that it's ever experienced, right? That's what those two concepts are. You'll see them in the context of the question. It'll make more sense. Yeah, I'll talk about that later. Okay. So this question asks for the 2-to-1 method. What we're doing first is we're finding the effective change in stress, usually denoted like that. One sec. Okay. So we read the question and we find that after we plug in omega, the average stress on the surface of the gravel is 350, which means it kind of looks like this, right? Stress is also like a loading. You can call this like surcharge or something. Right, so on the surface, that's how much we've loaded the gravel by. It's some kind of rectangular load, but we're using the 2-to-1 method. 2-to-1 method only works with a kind of like rectangular load, so you can think of it like a building or something is rectangular shaped, I guess, right? Yeah, it's given, this is a platform, sorry. So this is 20 across and then 10 in, I guess. And we care about a point in the soil that's 6 meters into the soil. Sorry, 6 meters into the clay. So here's where it gets important. So clay is not our top layer. Clay is wedged between gravel and sand. But when we do our calcs for the 2-to-1 method, we care about, the point of interest we care about is the middle of the clay layer. That's where we do all our consolidation settlement calcs from. Okay, so even though there's a gravel layer above it, everything, we care about the point 6 meters into the clay. Yeah, that's what we do the 2-to-1 method from. So that's 6 meters in this calc, right? Loading 350. This is base times length, right? So B is usually what we consider the smaller dimension, right? So you know how I said the platform was 20 meters by 10 meters? B would be the 10 meters one. 20 is the longer dimension, it's usually L. Right, we calculate that, we get 168 kPa. Right? Okay, next. Okay, so when we're doing, okay, so here's our point of interest, which is the middle of the clay layer, right? We want to find, oh, sorry, we've already done step one. We've gotten the change in effective stress, right? What we're looking for now is sigma dash I. Does anyone remember how we get this? This is just effective stress analysis. So it's that like bending moment diagram that's like vertical kind of thing, right? So here's where we actually have to account for the gravel as well. Because remember, we have gravel above our clay. So the weight of that gravel we can't forget about, right? So we have to calculate unit weights using our formulas. Oh, by the way, sorry, the water table's here. So we're considering this as dry, considering this is saturated. Yeah. So we're plugging in the formulas. 1 plus 0.5, 17.3133 kilonewtons per meter cubed. Similar thing here. except we're doing the saturated formula. 0.2 is given in the question. This is the moisture content of the clay. Right? The clay's heavier, right? Which checks out. Okay, cool. So now, we're going to add together these unit weights multiplied by the depths, right? So for the gravel, right, we have, sorry, the gravel is ZID dependent, but for my case it's 6 meters, right? The gravel layer is 6 meters deep. What number are we going to plug in for clay, for the depth of clay? 6 meters. We still care about the middle of the clay layer. For everything settlement related, we just care about the middle of the clay layer, except for the part, one of the parts is talking about point A, which is 4 meters deep into the clay, not 6 meters. That's the only time we deviate, right? So this gives us our initial stress, right? Now pore water pressure, this is just because the water table is here, right? So the water table is here, our depth of water is going to be 6 meters as well, right? So remember, to get the effective stress, we just subtract the total stress by the pore water pressure. Great, so we got that. Now the final, right, we simply add on delta sigma z. So that's from our 2 to 1 method, remember? That's 168,269, like that. So we have a increase in stress due to the loading of our platform, which makes sense, right? So we have the stress of what it originally was before the platform was built, and then we've calculated the stress, the effective stress of what it is after. Now these two numbers is what we're going to plug in order to get stuff related to settlement, right? Initial void ratio is another formula we have to plug in. Remember, 0.2 was our moisture content of our clay. 2.65 is just assumed. That's our initial void ratio, right? So I've got a question for you guys. When you compress clay, right, do you expect there to be more or less voids when you squish it together? Less, because all the air and water and stuff's getting pushed out as you squish together your clay. So essentially, when we're talking about initial void ratio, that's what the void ratio is before we do any loading and stuff like that to it, right? Yeah. And that's based on like samples that we've gotten of whatever moisture content we already had in our soil. So it's given basically, right? Okay, now the change in void ratio, here's where we start getting into the settlement specific, consolidation specific formulas. And we were given the compression index in the question, so that's 0.55 to answer what you're saying, Farhan. So CC was given in the question in this particular case, right? So by the way, compression index is to do with like when you load soil, and then rebound index is to do with when you wait. Is that right? Okay. Okay, I'm not 100% sure on that yet. Let me go back to that once we've gone to that point in the question. Anyway, so the ratio of your effective final stress and then your effective initial stress, that's what we plug in, right? So that was 335, 5604, and then this is 167, 2914. Great. You're expecting a change in void ratio in this rough, I guess like ballpark of numbers, right? Because that was the initial, the change should be something like that, right? As you're squishing it together. Okay, great. So H, right? H is kind of a concept that's only really used in this, sorry, so H here isn't head. It's not like water related. Oh, sorry, it's not seepage related. H is our compressible layer, right? And when we're talking about compressible layer, yes, like sand and gravel is compressible. What we're talking about is the consolidation specific compressible layer. In other words, our clay layer, right? That's what H is, right? So it's gonna be 12 meters. So that's 12. That is, we calculate it to be 0.16626. Calculate this to be 0.53, right? And that gives us 1.304 meters. Yeah, so just do a sanity check real quick, right? Our 12 meter clay layer is going to settle, right, squish by 1.3 meters. This is supposedly correct based on Clarissa's solutions, right? Yeah, you want something in that ballpark, okay? This is over a long, long period of time, by the way. Yeah, this is total settlement, yeah. Oh yeah, so gravel settles differently to clay. So gravel experiences something called initial or elastic settlement. It has nothing to do with this course. So we don't consider it as part of our formula for when we're talking about consolidation. Consolidation is more like a long-term settlement. You can think of gravel's settlement as like a short-term kind of, yeah, settlement. You know what I mean? Yeah, yeah, yeah. Yep.
Is that because gravel is above the
Yep.
water table, or if the gravel is below the water table, do we still take gravel as saturated or not really? Because I know
Yep.
gravel is behaving differently
Yep.
than clay.
Okay, yeah. So in the case where this is like the water table's in the middle of the gravel layer, you need to calculate the dry and the saturated gravel unit weight. He doesn't do that to you because it will take too long. But you'd have to add them differently because they would have a different unit weight. Yeah. I'm not sure which one's heavier. The dry or the, yeah, someone would have to do that calc, but yeah. Okay, cool. So now the question's asking for part B, how much would it settle after 6 years, right? So let's do a little timeline, right? So let's do a little timeline, right? Essentially, this is our total final settlement, right? And we calculated that to be 1.304 meters. So after 6 years, you'd expect that to be a little less, right? Yeah. Probably most of the settlement will happen towards the start, and then it'll plateau out, right? But we still have to calculate what that settlement will be at the 6 year mark. That's what the question is asking for. Does that make sense? Yeah. So now we have to convert 6 years to seconds because everything's to do with like the rates are to do with seconds. So you punch all this shit in the calculator. Everyone knows where those numbers are from, right? Like 365, 24, 60, 60. Yeah. Okay, cool. That gives us this number in the calculator in seconds. Okay. So CV is the coefficient of consolidation. Okay, it's given in the question as 6 times 10 to the negative 4 centimeters squared per second. Now, conventional wisdom will tell you convert this to SI units straight away, but it's actually easier to do this calc keeping it in terms of centimeters because the centimeters will be divided out, I think, later. Okay, just trust me on this. This will be faster. Okay, so DP, we're going to scroll back to my notes because I haven't explained this yet. DP is to do with the drainage path, right? And it's a rate of consolidation concept. So, you know, part A, we talked about what the total settlement would be. Now, rate of consolidation, right, is all about finding what the consolidation will be at a certain time that's not the very end. Do you know what I mean? And so we have to consider new concepts like drainage paths and stuff, right? Sometimes you'll see in the formula it's DP, which is drainage path. Sometimes you'll see it's HD, which is height of drainage. They're effectively the same thing. Okay. So there's two cases. The first one is you have a rock layer underneath, right? you're not going to have a rock layer above. And the second one is that you have a soil layer underneath, right? So based on our cross section from the question, do we have a rock layer underneath, or is it soil underneath? Yeah, soil. So we're going to have double drainage, okay? Which means our drainage path is only going to be half as long as our compressible layer of clay. Does that make sense? Okay, basically what I'm trying to say is it's 12 meters, which is the clay layer, divided by 2, 6 meters. That's for double drainage cases. That's when you have soil underneath, right? Now, instead of converting this to meters, you're going to have less trouble converting this to centimeters because they're going to be divided out anyway. So just convert that to centimeters, right? It'll be faster. Okay. Next, we have to calculate TV, right? This is a formula. This is this blue formula here. Yeah, here's where we plug in all our numbers basically. And we get a TV of 0.31536. Yep. And that's the number that we're going to pivot on this graph with, right? So we start here. We're going to hit the line and we're going to go left. That's going to give us U. So U is the average degree of consolidation for one dimensional settlement. This is one of the two methods that we use to calculate rate of consolidation, aka getting U, right? But it's what the question asks. I should probably show you the question actually. So question B. Okay, my bad. Okay, basically, if the question words it kind of generally, use the average degree of consolidation. Okay, but if the question, which we'll see the other method in a second, says we care about a certain point, we have to use our other method. Okay. Anyway, so we get a U of 0.63. It's kind of trippy because it starts from 0 and then increases down that way. But yeah. Whenever you're reading off one of these graphs, a man will be pretty generous with the margin of error. So if you got like points, maybe not 0.7. Yeah, you know what I mean. Like you're gonna be off by a couple decimals, and it's okay. So that's 0.63, sorry. This was from part A, right? So that's our final settlement, right? So you always have to calculate the final settlement before you can calculate what the settlement will be at an interval that's not the end, right? This should give you a lower number, and if it's giving you a higher number, you fucked up somewhere. Okay, cool. So let's go back to part C now, right? It's asking what would the effective stress at point A 5 years after the construction of platform be? Yes. Give me one sec. Yeah, and then it's also okay, sorry. Let's just do the question. Oh, sorry. So let me show you part A. Sorry, point A. Point A is 4 meters into our clay layer, right? So it's not in the middle. It's just a little bit above the middle of the clay layer, right? So it's going to change the way that we have to do things, right? So these were from previous parts, right? So we calculated what the increased stress would be due to the loading of our platform, the installation of our platform. We also calculated what the settlement was going to be at the very end, right? Now we have a new time. It said 5 years, right? That's going to give us this number in seconds. We're going to keep using CV. Now we're going to plug in everything again into TV. The only thing that really changed was the fact that we did it for 5 years instead of 6 years, right? But we're going to get a lower TV value, right? Now we're going to use isochrone's method, right? So you have to start using isochrone's method whenever you use whenever you're analyzing a point that's not in the middle of the clay layer, right? So again, our point was a little bit above the middle. So Z is going to be 4 meters because point A, that's the middle. That's the middle. That's point A, right? Point A was 4 meters, right? So that's what Z is. HD is the height of the drainage, or also called the drainage path, right? That's going to be 6 meters. Yeah, that's what we start with on the left-hand side here. So that's a ratio of 2 to 3, or 4 to 6, 0.667, right? Yeah, makes sense. Okay. Now STT, this is basically the settlement as a function of time at a certain point. Okay. And to calculate this, we need U as well, and then STF. Now, U is going to be slightly different. U is a function of the depth now. So it's a depth of 4 meters down. And that's why we need isochrons method from 4, right? So this line here is TV. So at a TV of 0.2628, right? We have to imagine where that line would be on the graph. Go from the left here, bounce to the line, bounce down. That gives us UZ. Make sense? But this is still a function of what our total settlement was going to be from part A. Yeah? I'm not even sure if this is what the question called for. Yeah. I'm not sure what happened. I think I'm just kind of copying Clarissa's solutions. For some reason, she answered STT instead of whatever the question called for. Yeah, sorry. Okay, so lastly, we have to calculate what the rebound index would be, right? So this isn't given in the question, and the rebound index is going to be calculated when you remove like a load, right? Like say we remove that platform, right? Okay, and then it also told us after removing the platform, our final depth was 11.35 meters for our clay layer. So if you imagine the clay layer, right, was 12 meters, like that. We originally thought that if we left it on for a very, very long time, it was going to be 12 minus 1.304, right? That's what we calculated in part A. But what it actually ended up being, because we removed it earlier than, the end of time, it ended up being 11.35 meters. So this is a different number, right? This number and this number will not add up to be the same. So that's what the rebound index is all about. We're going to see later we have a void ratio to stress graph, and then there's kind of like a line that looks like that and then that. So that is your compression index, that's your rebound index. It kind of rebounded at a different gradient, if that makes sense. Right, so CC and CR is to do with the gradient. Yeah?
Do we need to draw these, or can I just use the formulas?
Use the formulas. I'm just drawing it for explanation's sake. I think, yeah, you don't even need to draw it. I just drew it here for explanation's sake. Unless it specifically says draw plot, stress versus void ratio versus stress. Yeah, basically, we're gonna find that there was actually a difference of what we expected of 0.819 meters. Okay, that's the difference between these two kind of drawings that I did, right? So we rearranged the settlement formula for the change in void ratio. Okay, that gives us this. Yeah, we plug everything in. Now STF is our difference now, right? Because we're trying to calculate the rebound index. The initial void ratio is a matter of that formula that was to do with the moisture content and the specific gravity. And H was our compressible clay layer's original height, right? So essentially we had a change in void ratio of this much, right? So that's what this is. That purple, yeah, that purple dimension there is that much. Okay. So we rearrange for CR because we're solving for the rebound index, right? And we plug these things in like that. These numbers are back from part A. Let me just write it down first and I'll explain why. Okay, basically, right, the final and the initial are swapped around. Because what do we actually do? We remove the platform. So it returns to its initial stress, right? But we have to consider that as the final stress now, because in the context of what we did, the final stress is going to be lower than our initial stress. Our initial stress was what stress it was when we loaded it, right? Does that make sense? And then that's the end of that question. I'm not doing good for time, guys. 12:50. I had one more question to cover. What do you guys reckon? Should we just keep going? Triaxial test. Okay. Triaxial test is cooked. That's all I'll say. I didn't have that much time to prep for it, but I'll try my best to explain it anyway. So the first thing you have to do is to do with the Moore circle, basically. I'm sorry, I'll rip that Band-Aid off right now. It's to do with Moore circle, and it's to do with Moore Coulomb failure criterion. So you're gonna see graphs that look like Moore circles with fucking lines going like that. Okay. So there are many different. There's three actually. There's three types of triaxial tests. You have consolidated undrained, which is what we're gonna cover. I think you have. Yeah, there's other ones basically. Yeah, this is the one we're gonna cover. All this information is going to become relevant, but in later parts. The most important thing you have to focus on at the moment is what the cell pressure is. Guys, just a bit quieter, please. Okay. The cell pressure is basically, for your Moore circle, it's the principal stress on the left, right? That's that. The back pressure comes in a later stage, but it's to do with pore water pressure, how much excess pore water pressure you have, essentially, right? That's kind of not required in part A. The total vertical stress on the sample before it fails, that's what your sigma 1 is. It's what your major principal stress is on your Moore circle, right? And we're also given the drain condition strengths for the soil, right? So we have a clay. That clay, let me just quickly draw this right. Basically, this is Moore Coulomb criterion. Moore Coulomb criterion is basically talking about it's a way to express how strong a soil is, right? Basically, most soils will fail in shear, right? So I'll give you an example of shear. If I had like a heavy painting or something that I put onto this wall, a poster or something, and I put a bit of duct tape to hold it up, right? It's gonna fail in shear if the painting's too heavy, right? Shearing is, that's what happens with soil, essentially, right? Shearing is, yeah, like you have two surfaces and they slip against each other, right? You're gonna see when you look at slope stability as well, slip planes for soil generally look like this, right? They could be semicircular or circular like this. There's also, like, say you have a sharp cliff and the soil will slide like that as well. soil usually fails in shear, right? So it's very important to understand the shear strength of soil. Triaxial test is related to finding out how strong the soil is, and slope stability is kind of like an applied version of that whole like Moore-Coulomb concept, right? Okay, basically we're given this and this. These are kind of soil properties which are related to its strength. Cohesion is to do with how sticky something is, right? Usually gravels and sands aren't that sticky, right? Most of the time they don't really have a cohesion, but clay does, right? Clay can stick to each other. It's like blue tack or whatever, sticky tape, something like that, right? Friction angle is to do with the particles' friction, like sort of it's to do with the particles' friction with itself. So one way this is measured is if you like dump a bunch of sand, for example, right? There's more like formal ways of doing this, right? But you dump a bag of sand and it forms this kind of hill, right? I believe that, or maybe it's the inverse angle. That should be the friction angle. It's the angle that it's able to kind of slope. Do you know what I mean? So a higher degree of friction angle means that it's stronger in friction. So clay will have both cohesion and friction angle as part of its expression of strength, right? So triaxial tests are usually performed on clay because they have this kind of property. You're going to see something as well called a direct shear test. That's generally performed on gravels and sands and stuff because they don't have cohesion, and you don't have to account, like basically those tests don't work when you have cohesion, right? Okay. You know what? I don't think I have time to like physically write out every step, so what I'm going to do is I'm going to go back to my notes and just point at them, the already written out version. This is a formula that you're given, so there's a couple, yeah.
Isn't C-0 for normally consolidated clay?
Maybe, I don't know. Just check yourself, yeah, I don't know. Okay, so basically, sorry, this is to do with circle geometry here. So this is, so when we're plotting like more circles and stuff, right, we're doing it on the plane of tau and sigma, right? Yeah, when we have this failure line that runs through, right? And this is Moore-Coulomb criteria. So that's that formula I wrote before, right? Yeah, basically they found this formula through, this is sigma 3, this is sigma 1, this is your friction angle. And then this y-intercept to the start of the line, that's cohesion. Okay, that's where everything comes from. Okay, I'll leave that there for a moment. We rearrange this, right, and we can get the version. So this version is to do with our effective stress. But all I've done here is I've basically said the total stress minus the pore water pressure is the effective stress. Plugged everything in. Here's the other version of it, which is to do with our total stress. Now, that's important because this first part asks, the first part is to plot the Moore circle, but it's actually easier to do part B first here. So we're actually working out the pore water pressure first, okay? So we were given this in the question, right? So remember when I said we had our total stress that the triaxial test failed at, and then we also said we had cell pressure. Those are where we plugged in like orange and blue. And then purple is where we plugged in our soil properties like this. We're rearranging for you, okay? That gives us our pore water pressure. We can work backwards from that and get our principal effective stresses, right? So one of these circles is going to represent the effective stress, and one's going to represent the total stress. The one on the left is actually going to be the effective stress, and the one on the right is going to be our total stress. So it's a little bit higher because this difference between these two circles, right, is our pore water pressure, right? We've just shifted it by the pore water pressure. But the failure criterion, this line, it all relates to the circle, basically, right? this circle and this line. Yeah. But since we want to plot everything, we want to be able to plot both circles. Do you know what I'm saying? Here's what the plotted Moore circle looks like, right? That's basically everything that I've been mentioning. Yeah, you can calculate these angles as well based on your understanding of triangle geometry, right? So that's based on 28, 62, and like 118 and stuff like that. Okay. Now, C says calculate the effective normal stress and the shear stress on the failure plane. So what that means is, remember your failure plane is your Moore Coulomb criteria line, and what we care about is the point of intersection, right? Here between the line and the stress, the effective stress circle. Okay. Essentially here, right? We can plot it, and we're going to call it sigma failure dash and tau failure dash. Sorry, let's put a dash there. Yeah, hypotenuse, triangle geometry, that kind of thing. We can work out everything based on angles, and we're solving for tau and x. So x is in the normal stress direction, but it's not what the failure stress is. It's, we have to find the center of the circle. This is what the question is asking for, and this is what the question is asking for, right? We care about these effective axial stress and shear stress quantities, okay? What should I talk about next? Sorry, just look at this one. That doesn't take that long to see. Skepton parameter is pretty complicated, to be honest. There's like a couple of nuances to do with it, but for the context of this question, it wasn't that hard to understand. Basically, it's given in the question that the soil is fully saturated, which means that your constant B for your Skepton parameter is 1. If it's not fully saturated, there's another formula you have to put in for it. Because it's 1, A, which is your Skepton parameter, is equal to A hat. A hat's a intermediate step, but in this case, it's what we're working out. It's the same thing. So that's A as well. It's your increased pore water pressure divided by your change in axial stress. Divided by your diameter of your Moore circle, basically, right? So increased pore water pressure, this is where back pressure comes in. So in part B, we worked out what the pore water pressure was, right? Back pressure is kind of excess pore water pressure, and it's given in the question. It's given in data. In this case, it's negative, and sometimes it'll be positive. So OC clays, over consolidated clays, will give you a negative number probably. I'm saying probably because I'm 95% sure on that. And normally consolidated clays will give you a positive number for this. So when you look at stress paths, right, the best way to look at stress paths is probably, the lecture slides are pretty good for it. I should probably also bring up, you can go on Linktree, Sigma Lectures, this is my notes. And there's soil mechanics. It's also the QR code that you scanned as well. These are my friend Barney's notes, they're really, really good. And this zipped file has all the workshop solutions as well. They're really good. His notes on stress paths are pretty good, I remember. Yeah, so just have a good look at this basically, and look at Precious stuff as well. Yeah, Q and P is basically, okay. So basically, as we change the pore water pressure in our triaxial test, right, these circles are going to shrink and grow and whatever, like that. Stress paths is basically mapping the top of the circle, the apex of the circle, and then that line. So you'll find the coordinates of that is related to P and Q, right? P and Q. P and Q have these formulas. So one is the average of the circles, right? So that's in the x direction, and the other one here is the radius of the circle, so that's in the tau y direction. This is all circle geometry and like more circle stuff. I know it's really like annoying, but like yeah, just try your best to kind of wrap your head around it. I don't fully understand it, to be honest with you. I'm just running through like step by step. Keep in mind on your PQ graph, you're going to have slightly different naming conventions than on your normal tau versus sigma graph, right? On your PQ graph, your angle is going to be this instead of this. So one's psi and one's phi. I don't know which one's which, the Greek letters. And then here, this is going to be A instead of C, right? So you're just going to have different constants. It's going to look a little confusing, but it's fine. You'll figure it out. This line here is the total stress path, which is the circle here that was graphed out, like that. And then it's shrinking like that along this line. This straight line here is basically the total minus the pore water pressure stress path, okay? So that's kind of what you'd expect your effective stress circle to look like. However, in reality, it actually follows this curved line, so that's the effective stress path. So it doesn't linearly move like that. So when I was talking about an OC clay and the fact that your Skepton parameter is negative, that means that it kind of bends this way. For a normally consolidated clay, it will bend the other way, right? So your stress path will kind of curve a different direction, if that makes sense. You'll see examples if you scroll through the lecture slides and stuff like that. It's so hard to cover all this topic. It's really like there's no like catch-all for all this stuff. There's like at least 5 different like versions of this basically, right? And lastly, it's talking about direct shear test. Direct shear test is more or less based on just Coulomb criteria's formula, and you work backwards and then want you to find the pore water pressure. Okay, now the last thing I'm going to talk about because I'm running out of time. Right, wait, guys. 5 more minutes, just trust me. Yeah, so slope stability. I don't have enough time to fully cover it, but I'll try to set you guys up so you can revise it and it won't be too painful. The idea of slope stability is that basically it's only geotech related or soil related. In no other course will you do anything to do with stability, except maybe you covered it briefly in 1300. There's 2 types of stability failure, right? Sliding and overturning. There's different names for it, right? They're based on Newton's laws. They're like fundamental physics, right? Sliding is usually to do with friction. Overturning can be to do with friction, and in the case of soils, it is to do with friction, right? But this is based on bending moments, right? So, what do I mean by stability? Stability is slightly different to strength. So if you've done concrete, which some of you guys have, some of you guys haven't, concrete beams or whatever, if you apply enough force to them, they might break, something like that, right? That is a strength failure. That's like a material actually like ripped apart and stuff like that, right? Now, if I have the same concrete slab, and I don't want it to move, I don't want it to slide, and it's against another object like the ground, and you push it in a certain way, right? It's static until it isn't, right? So why I'm talking to you about Newton, right, is that stability is about that interface between static and dynamics. So essentially, an object's not moving and then it moves. That's what stability is about, or that's what instability is about, right? So if I'm pushing against this slab or whatever, concrete slab, and it starts sliding, that is a sliding stability failure, right? I'll give you another example. Same concrete slab, and it's teetering over this edge, right? Maybe it's like this. And it falls due to the wind. That's an overturning failure. That's a point of rotation. The point at which it overturns, and like the not external, it's called the disturbing moments. when the disturbing moments overpower the resisting moments could be like the weight of the beam or whatever. That's instability, right? So soil mechanics version is going to be more similar to the moments one, right? Because usually we're going to be dealing with, this is what you'll see on the slides. Usually we're going to be dealing with slip failures like this, right? And it's all going to be around this point O. Point O is the center of rotation, right? But you'll notice, and the reason why I talked about a concrete beam breaking, even in the context of a concrete beam, the material itself didn't actually rip apart. It's not a material failure. It's all to do with forces causing it to become dynamic or like moving, right? Whereas it started as static. So when we're talking about it in the context of soil, right? This soil, it's static. It's not going to move, right? But if you put a building on it like this, it might slip and become a dynamic moving system. And we don't want that because that's dangerous, obviously, right? It's like, yeah, that's what instability is, essentially, right? And the other thing, and why, sorry, I drew these arrows the wrong way. Why we care so much about tau, right? We're obsessed with tau, Moore, Coulomb criterion. It's because tau kind of behaves like, it's a material property, right? It's the strength of the soil, but it behaves similarly to like uniformly distributed loads. I know that sounds a bit weird, but do you remember in like 1300, uniformly distributed loads were these ones, right? So its units were like kilonewtons per meter or whatever, right? So in one dimension, tau behaves like it's usually like kilonewtons per meter squared, but if we're looking at it in 1D, kilonewtons per meter, we have to multiply the shear strength of the soil, which is a material property, by the arc length of the slip. Right, so R is the radius. That angle is alpha. The arc length, let's call it L, right? So L is R, and then alpha is in radians. In order to get this, the frictional strength, I guess you can call it, the frictional strength of the soil is basically tau, which is a material property, multiplied by the length, which is resisting, right? So you can imagine more length means more soil is kind of resisting it in friction, like that, right? That's going to give you your resisting moment, right? Okay, but we're not done yet because we care about overturning. Overturning is to do with moments. So all we've done is gotten the frictional force resisting. I don't know, I'm kind of just yapping right now, but like, sorry, one second. In terms of moments, right, what we care about is multiplying it by the lever arm that it acts over. That's what is going to give us our resisting moment. Okay, that's the first part. The second part is the disturbing moment. So disturbing moment are things that are going to cause it to destabilize. For example, this building. Sometimes it's the weight of the soil itself. So let's just say, let's take the building out of the question. But let's say the center of mass of this whole soil body is here, right? That's its lever arm. Do you get what I'm saying? So this is going to push against the soil and cause it to slide, right? And if these numbers don't line up the right way, the disturbing moments are going to overpower the resisting moments, right? Now the factor of safety, which I yapped about a bit earlier, is basically how many times greater your resisting moments should be than your disturbing moments, right? Usually it's in the ballpark of like 3 or something, right? So you want 3 times as much resisting moments as disturbing moments, right? So yeah, anyway. I'll leave this up. I'll also add this page to the soils recap, and this is going to be recording on YouTube. So yeah, anyway, that's the end of my soils recap. All good. Good luck for your exam.
Thank you.